Uh, I would like to introduce Muhammed Gökmen from Bilkent University, and he's going to talk about the basic theory of Hilbert modular surfaces. Yes, Muhammed.
Thank you, Kaan. I should first start by thanking the organizer of this event for giving us the opportunity. I should thank my mentor, Kaan, for introducing me to this subject. Our original project report contains much more, but in this presentation we'll be mostly limited to the basic construction of Hilbert modular surface X gamma, which is associated to some group gamma. So we can start by defining a few preliminary facts. We take F to be a totally real quadratic number field, something like Q adjoint square root of B, that being one number. And we can embed this number field F into R2 via these two Archimedean places, sigma 1 and sigma 2, but these are like F has two automorphisms, and so they correspond to those. OF is a ring of integers, and we have the units of the ring of integers. And we also have the ideal class group of F. We denote it by CL, which has order H of F. It's the ideal class number of the number field. We can write the ideals of F. The fraction ideals form a group in themselves that's given by ideal multiplication. We have, of course, integral ideals, but we also have fraction ideals. And any fraction ideal can be written in the form of alpha OF plus beta OF for two alpha and beta. We don't denote a positive element. This should be a totally positive element. A totally positive means its image under both the sigmas positive. Of course, each sigma sends to the real number, so there is order defined. Just like we embed the number field F into R2, we can embed the special linear group of F given with elements from F into SL2R squared using the previously given to sigma 1 and sigma 2. And using this in embedding, we can define an action of SL2OF on H2. This H is the Poincare upper half plane, which means the upper half of the complex plane where all the imaginary parts of the numbers positive. We call this group SL2OF the full Hilbert modular group. I take here the quotient with the the group of order 2 plus and minus identity matrix, but this is because this is not necessary, but the image of any element is the same with under the matrix and its additive inverse, so gives us sort of reduces the group, makes it more smaller, but it's not too important. And that group was the full Hilbert modular group. When we take the elements from OF, we define a more general group, gamma, where it's a subgroup of SL2F. Now, not just the ring of integers, and we take it to be commensurable with gamma F. This is the full Hilbert modular group. It means that it has a finite index in both gamma and gamma F. The intersection is finite index in both gamma and gamma F. Now, this makes gamma act on H2 properly discontinuously. Now, this the given definition given here is also true, but you can think of it as if 2 points have different images under a matrix, and then they also have neighborhoods that don't intersect under the same matrix. We will construct the Hilbert modular surface, and to do that we will first consider this quotient space H2 mod gamma. Now, what this means is we look at the points in H2 and consider their orbits. We look at the orbits of H2 under elements of gamma, and we sort of identify all the points that lie on the same orbit. So in this way, 2 points that have the same. If you can transform one point to another using an element of gamma, it means they're in the same in the same equivalence. We define an equivalence relation essentially, and then we can think of this. So this is the Hilbert modular surfaces is the case in 2 dimensions. Now there's a 1-dimension analog of this, and what we do there is we take the action of SL2Z on H, and there's something called a fundamental domain. Fundamental domain is essentially where every orbit of H has a single representation on the fundamental domain, and it's a bit like it's a vertical strip that extends up to infinity, but it's terminated at the base somehow, and you can sort of take that strip and sort of glue its size and the bottom to make it a sort of a disk, and then you can also sort of turn it into a sphere. But in the 1-dimensional case, the strip extends to infinity, but the infinity itself is not on the upper half plane. If you try to make it into a surface, there will be 1 point missing. And this prevents the quotient space Y from being a compact space. And that missing point is what we call a cusp point. Now, in 2-dimensional case, it's very similar. We don't necessarily we consider the this as the analogous quotient. And by the way, we don't define gamma as gamma f. It can be any subgroup, so we can have more than one cusp. We can have different cusps. We want to make this space compact space. So to do that, we will look at the action of gamma on P1F. Again, if we think of this in terms of the 1-dimensional analogy, you can sort of convert the point at infinity to any rational number using a fractional linear transformation. Does that make sense? Sort of, you take a number, for example, a, and then what that means is infinity and all the rational numbers are in the same orbit. Similarly, in the 2-dimensional case, instead of taking P1 cubed, you take P1F, and these act as the F rational boundary points for H2. I forgot to say, you should think of the point across plane and the rational numbers set and the point at infinity will act sort of like the boundary of the polar plane. Again, the Q1 cube is essentially Q adjoined infinity, and this is kind of the same, F adjoined infinity. And then we will look at the action of gamma on P1F, and the orbits of P1F will turn out to be the missing cusp points in the previously given surface Y gamma. And there's a very important result that we need to mention here. And so when we take the full Hilbert modular group, gamma F, and its action, and we look at its action on P1F, and the number of orbits, or we could say the cusps, are in a bijective correspondence with the ideal class group of OF. For example, the rational numbers have a single, their ideal class group is trivial, the 1 element, and there's only one cusp, infinity. You can convert infinity to any rational number. This is a 1-dimensional case, and in 2-dimensional case, we can have more cusps, and they are in bijective correspondence with the class number of F. We call these orbits cusps. And then what we do is, instead of looking at the quotient H2 mod gamma, this should be H2, my mistake. we look at we define this H2 star. We take the union of these two. Before we go on with this, we need to define a topology on H2 star. H2 star is sort of, again, if we think of the sort of one-dimension case, it's like the H2 star is a topology that when we look at just H2, it's the same Euclidean usual topology, but we also have these the rational boundary points. So it will be like the rational numbers has a single cusp. So we need to only think of infinity, and we add to the usual topology the base of open neighborhoods of the cusp infinity, and that gives us a topology on H star in the one-dimension case. And again, in the two-dimension case, we do a very similar thing. We get a base of countable base of open neighborhoods of cusp infinity, and we also define the same neighborhood for the other cusps. And these cusps, by the way, we can transform one cusp to another using a transformation matrix we take from S up to F, essentially. And this gives us an appropriate topology we can work with this. And this is important. It's called a Satake topology on H2 star. It allows us to compactify the previous surface Y gamma. Now that we have defined an appropriate topology, X gamma is a compact surface. This X gamma will be important, but we first have to look at the Hilbert modular forms. Again, these are, so you can think of these analogously to the one-dimensional case. The classical usual modular forms have a single variable. Hilbert modular forms have two variables. Hilbert modular forms are meromorphic modular forms defined on H2, and they have complex values. And they're defined for a gamma, and they have a weight K, K1 and K2, and they have to satisfy this equality. This bit in the middle is called an automorphic vector, which is called the transformation formula. If it's holomorphic, we also say it's a holomorphic Hilbert modular form. And you can sort of see that this function f is sort of, in a way, gamma invariant. Not exactly, but it's almost gamma invariant. It doesn't change under the action of gamma. Its value doesn't change. This will come up later. But we call the vector space of holomorphic Hilbert modular forms nk gamma. Then we have this group itself is not too important, don't get confused. But essentially, what this tells us is, under the action of this group, we have this equality. Mu comes from M. M is, by the way, a lattice. It's like a Z module of rank 4. It defines an additive group, like a cage. So now this equality told us that we can define Fourier expansion of f, and we write this Fourier expansion around the cusp infinity. The Fourier expansion with Fourier coefficients a sub nu, and the nus come from the dual lattice of the previously given lattice M. The dual lattice is given with respect to the trace form. After we give a Fourier expansion, that's a very important fact. It's called the Gauss-quadratic principle, and it says that for a Fourier coefficient to be non-zero, for it to non-vanish, if a sub nu is for it to be non-zero, nu has to be either totally positive or exactly zero. Totally positive means all of its images under sigma 1 and sigma 2 are both positive. This is important information, and in contrast to the case that's one-dimensional, it means that any holomorphic Hilbert modular form that is holomorphic on the Y gamma. I mean, before we had made the compactification, it's also holomorphic at the cusps. This is not the case in one dimension. You will remember the Fourier expansion. It starts off with a new S to be either 0 or positive, so with A0 plus, then the rest to the positive A news. And then we say that if you plug in Z equals infinity, you will only, the sum will all go to 0, you only get A0. So we write f of infinity is A0. We can also write the Fourier expansion of around the other cusp points. Again, as in the previous Sadaka topology we can use the transformation matrix M to convert f to the we use transformation matrix M, and then we look at the Fourier expansion of this function at infinity. It's like a conjugate group of the original gamma. This notation, by the way, is called a slash operator. It's written like this. Instead of in the original definition, we had positive K1 and positive K2. Now we have negative K1 and negative K2. You can put in a gamma that makes Z go to the stay in the same orbit. It doesn't change the outcome. Another point is that this expansion depends on the choice of n. We have a few facts about the modular forms, but I think I'll skip these because I'm nearing 18 minutes. One of them, for example, is that if K1 and K2 are different, F must be a cusp form. Cusp form means that it vanishes at the cusps. Now, this is sort of important because the cusp forms define a vector subspace of all modular forms. And it's a very simple proof. I'll skip it. It comes from the Colbert principle. Again, I think I should skip these. And I don't have too much time to talk about this, but the bigger picture going on here, and it's that we look at this surface we constructed x gamma. I mean, it's acts as a domain for the Hilbert modular forms, but it's also a moduli space for something called abelian varieties. An abelian variety is a complex torus of dimension n, and it admits a projection and an embedding into a projective space P and C. And to embed these, again, by the way, in the case when n equals 1, any complex torus always admits an embedding into the projective space, but it's not the case in higher dimensions. So we have to make them be able to embed into the projective space, and they're done via the global sections of an ample line bundle L. Sort of embedding into projective space is also sometimes called a polarization. This X gamma is we in our project we interpret it as a sort of a moduli space for abelian varieties of dimension of abelian varieties. Sadly, I don't have too much time to talk about these, and I don't really know them that well myself, I have to admit. Yeah, but if you see our report, you can see more and learn more about this. Any questions? I think I'm done.
Thank you, Mohammed.